everybody. I'm very happy to be in this very nice conference. Thank you for organizing it. And the subject of my talk is calculating the adsorption energy of a charge adsorbent in a periodic metallic system. Just, okay. When do we need such calculation? Let's say when we do heterogeneous catalysis, the reactants are adsorbed and the products are desorbed. And if one of the reactants is charged, we need such calculation. A special group of such calculation is electrocatalysis, in which the extra charge is transferred through the electrical cycle to the other electrode. So as a matter of fact, there are two ways of doing this calculation. One way is, as I told you, one separate class is the electrocatalytic reaction in which a constant potential is applied. The current transferred the charge from the electrode, from one electrode to the other, so the charge of the considered slab is not changing during the process. And we calculate the energy of the electrocatalytic reaction by shifting the energy by minus EU. U is the electrode potential. This is Norskov method. But if we don't have a electrical cycle, the slab is charged, the current is, the extra charge is not transferred to some other place. And we can do this calculation in two ways. One is the cluster approach, in which the catalytic surface is modelized by a cluster. The cluster, this is a limited, the cluster is limited to finite number of atoms, so there is no periodicity. And this method has a lower reproducibility of experimental results. Of course, people do it and find the important results. This is, for example, a reaction by Gomez group. They used a cluster of 12 copper atoms to calculate the adsorption energy of the halides, F minus, chlor minus, bromine, and iodide. But if we want to modelize the system in a more realistic way, people used a system with periodic boundary conditions. But in this case, the number of electrons is not compatible with the number derived from the valence and the number of atoms as the system is charged. So there are some problems. The main problem is, not the main problem. One problem is the energy convergence that is very slow with respect to the size of L of the supercell. But the most severe problem is a homogeneous background charge that is assumed, and it causes artificial states in the vacuum. So total energies from charged slab calculation are useless. We use VASP for our calculation, and in the VASP program, there is a keyword named NELECT. The default of NELECT is the number of valence electrons, and in this case, the system is neutral. But if we are talking about a charge adsorbent in a periodic system, in this case, NELECT is not equal to the number of valence electrons. And I quote from the VASP wiki, this is the VASP's manual, and they write if the number of electrons is not compatible with the number derived from valence and the number of atoms, a homogeneous background charge is assumed. And I go on quoting, the energy converges very slowly with respect to the size L of the supercell, and the total energy depends linearly on the width of the vacuum due to the interaction between the charge slab and the compensating background. Presently, no simple posteriori correction schemes is known or implemented in VASP, so the conclusion is that total energies from charge slab calculation are useless and cannot be used to determine relative energies. And I must say that the main problem is when we have a metallic surface. The problem is with any surface, but with the metallic surface, the problem is more severe because with a non-metallic surface, we can treat the charge as defects in the slab. But when we have a metallic surface, due to the conductivity, the whole slab is charged. So what can be done? As a matter of fact, the convergence problems are solved by work of Markov group and Neubauer group, and people also try to solve the problem of homogeneous background charge. And you see here is a list of people who have done it, and this is only a partial list. What people used to do is to modify the Coulombic potential and change the algorithm used for calculation, mainly the Poisson equation. But this is very problematic because these corrections are implemented only in limited number of programs and they are not applicable for all systems. So for each system, we have to look which correction is good and which is not giving us good results. And as I told you, for metallic system, there is not a good correction scheme. So what can we do? So if we cannot, if we cannot calculate directly adsorption energy of charged adsorbent on metallic system, we looked for some bypass and we decided to modify the scenario and we used a counter-ion. We call our method counter-ion method. This method is based on 3 principles, and we have to take care of all these 3 principles, otherwise we cannot rely on the results. This is Basil Raju, that is this is the student that is involved in all this research. He has done all the calculation. So first of all, we put a counter-ion with an opposite charge in a non-interacting distance in the vacuum. And we replace the vacuum by aqua solution using an implicit self-consist electrolyte solvation model. We use VASP-SOL. This is important to ensure an ionic model. And the last thing that we do is we perform a charge analysis. We use Bader charge analysis to check that indeed the ionic species studied remain charged. So the scenario is like this. Here we have metallic slab. This is, here we adsorbed an anion, and we put here a counter-ion, let's say sodium. If this is -1, sodium is +1, and it is far enough from the anion and from the above metallic layer. We replace the vacuum by aqua solution using VASP-SOL, and we perform Bader charge analysis. And the charge of the sodium here should be +1. If this is +1, okay, our system is what we mean it to be. The anion, you see, that is adsorbed, there is some charge transfer from the anion to the metallic layer. Therefore, the charge of the anion may be less than -1. So, well, just one moment. Yes. This is our method, but how do we know that it works well? We have to do some validation. We followed in our validation what other people have done. Here, this is a method published in 2021. They have some graphite with carbon and nitrogen, and they want to form their charged vacancies. And they show, this is the formation energy, and they show that without the correction, the formation energy is increasing as the vacuum size is increasing. But with their correction, and these are all kinds of correction, they get a straight line, the formation energy is constant. Another manuscript that we found is a work of Bell and Nates that was published in 2018. They also have a graphic structure with charged vacancies, and they wanted to absorb CO2 on this slab, and they what they have done, they removed the periodicity in the direction, and they show that the absorption energy is constant with the vacuum space. Without this correction, the adsorption energy is increasing with the vacuum space. What they have done, they plot the adsorption energy versus the inverse vacuum space. These are the blue points, and they extrapolate the line that is passing between this point to 0. 0, it means infinity vacuum space, and then they get exactly the same value as with their method. So what did we do? First of all, we wanted to be sure that we get a correct charge and energy when we have only 2 ions. We took a ion of borohydride and the counter ion sodium ion. We place them in a box without a metallic surface, and we vary the distance between them. And you can see that the energy is constant. It doesn't depend on the distance. And also the charge is constant. This is the charge of borohydride. It is -0.96 instead of 1. And this is very good. We also try the method of the extrapolation method. So here the red points and the line is our result with the counter ion method. We see that the adsorption energy is constant. In this case, we adsorbed H- on a silver surface. And the blue point is what we get without correction. We extrapolate the line that is passing between this point and it to 0. As I said, it is a vacuum distance of infinity, and we get a very close value, not the same. And that is clear because if it is very, everyone can see that the blue points are not lying on a straight line. So we took only the 3 last points, and we get, and we extrapolate the line that is passing through them, and then we get exactly the same value as we get with our method. So we can say that our method is good. Oops, no, here. We used our method to calculate adsorption energy of several ions on a silver surface. And if the vacuum distance is larger than 16 angstrom, that is a normal vacuum distance, we get straight lines, as you see. The adsorption energy is not dependent in the distance between the slabs. I want just to go back here. You see this point here, the vacuum distance is 50 angstrom, 75 angstrom, 100 angstrom. We cannot do such calculation. They are too time consuming. But 60 angstrom is really normal. We used this method to calculate the hydrolysis of borohydride on silver surface, and in another manuscript we have done it to study the hydrolysis of borohydride on a gold surface. We published this method a year ago, and two other groups used it this year. One group used it to calculate the adsorption energy of formation on a metallic surface. The other group used it to calculate the oxalation on a non-metallic surface. And I believe that this method will be used further. I would like to show you some results, but to make things long story short, we'll go just to the concluding here, the concluding graph. Here we studying the mechanism of the hydrolysis of borohydride on silver. This is the blue line, and on gold, this is the brown line. So we can see that first step of hydrolysis is a higher barrier, then we get BH3OH minus, the blue line is silver, then the other step of hydrolysis have a significant lower barrier, and we get BH2OH2 minus, but then an hydride is released spontaneously, and it is adsorbed to the surface, and we get BHOH2 twice. The adsorption energy of this species is 0.21 eV. It's not very large, but what you see that the barrier for the third step is higher, and for the fourth step is even higher. So we believe that BHOH twice is dissolved from the surface, and not all the hydrolysis is not completed on the surface. In solution, this is a the hydrolysis is a very slow process. On gold, the mechanism is quite different. The first hydrolysis step to form BH2OH minus is composed of 3 steps, as you see in one. First of all, we get BH3, and then it reacts with water, and finally hydrogen is released, and we get BH3OH minus. Here, the second step is very similar to what's going on silver, but then the hydride is released, and we get a very exothermic reaction, and we get BHOH twice. The adsorption energy on gold of this species is large, 0.67 eV, and this is stuck on the surface. The third step of hydrolysis is endothermic, so no more hydrolysis is happens on the surface. As this is so strongly adsorbed, it occupies adsorption site and it prevents more borohydride molecules to adsorb at the surface, and some of them stays in vacuum. These are experimental results that we were very happy to be able to explain with this mechanism. First of all, here the hydrogen yield is measured as a function of time when silver nanoparticles and gold nanoparticles are used as a catalyst. The red line is the silver nanoparticles are the catalyst, and here we see that on the silver surface we get about 66% of hydrogen yield, no more. And then when acid is added to the solution, 100% yield is accepted, you see, is gained. And that's because we believe that BHOH twice is dissolved and it is hydrolyzed in the acidic solution. In presence of acid, the hydrolysis is very fast. But when we talk about the reaction that is catalyzed with gold nanoparticles, on the surface, we just get about 50% hydrolysis and no more, because we said we are stuck here. When the acid is added to the solution, there is some more hydrolysis, again, 60–70% of hydrogen yield is gained, and that's because borohydride that was not adsorbed on the surface reacts, but we do not get 100% yield, and that's because the borohydride on the BHOH twice on the surface is very stable and is not hydrolyzed even in an acidic solution. So this is really very strange results, and we are happy that we can explain them. And finally, I would like to thank all the people that were involved in this research, and of course, I want to thank you for listening. Do you hear?
Okay. Okay. I have a short question.
Yes.
Aside from beta charge, did you also check the local potential between the counter ion and the surface? Because I think a little bit close that the electric field change between the counter ion and the surface is a little bit dramatic than in the real situation.
Can you ask again? I didn't just ask about copper ions.
Yes, about the counter ion. I think you confirmed the charge separation based on beta charge analysis. Beta charge analysis.
Yes.
Yes, and did you also check the local potential that I mean the electric field between the counter ion and the surface, because maybe the two different charges is too close to than the real environment, so that the electric field change becomes a little bit dramatic than the real situation.
You see, we didn't check it, but of course, as I said, we need a minimum value of the vacuum space. Otherwise, the results are not very good. As I said, we need at least 16 angstrom, and otherwise, the results are not good, but we didn't check the potential.
Okay, I see. So let's thank for the speaker again.